Let me start by saying that quantum field theory perhaps is one of the greatest achievements of the theoretical physics of 20th century. And the quantum field theory, in fact, arose from an attempt to combine two already existing and experimentally verified theories. One of them is a theory of special relativity, and the other is quantum mechanics. And if somebody asks you, what is quantum field theory? That the answer should be that quantum field theory is a unique tool which is used to describe the physics of elementary particles. So it's a theoretical tool. It's a tool, simply a tool, and it's a unique tool which we have at our disposal to describe the physics of elementary particles. And as you know, probably, that quantum field theory stands today under numerous precision experiments, precision tests in colliding experiments, like, for instance, those which people carry out in the Large Hadron Collider at CERN, or, for instance, at Fermi National Accelerator Laboratory in the United States. But methods of quantum field theory actually have universal character. And they are not only applied to particle physics, but they are also widely used, for instance, in theoretical condensed matter theory. And so you find probably, if you go to the library, you find many books where the methods of quantum field theory are used in condensed matter physics. So if you are going in the future to do something related to condensed matter, then it's very, very helpful and useful to know something about quantum field theory. Because, as I say, the methods are universal in the sense that they are applied to dynamical systems with a large or infinite number of degrees of freedom. So whatever you have a system with a large or infinite number of degrees of freedom, then this means that quantum field theory is somewhere around. And I should probably say that still, in spite of being very well developed during decades, actually, starting from 1928 discovery by Dirac of the theory of the electron, still today, we cannot say that quantum field theory represents a completed piece of knowledge. The theory is still under development and is still under precision tests. And in fact, it still occupies the forefront of modern scientific developments. Now, describing behavior of quantum fields, as I said, we necessarily deal with systems with large or even infinite number of degrees of freedom. And this leads to a certain well-known problem. Namely, because you deal with infinite number of degrees of freedom, some of the physical observables, something which you would like to know, because it is important, some of the quantities you would like to measure and predict, they appear to be, from theoretical point of view, given by divergent integrals. So you compute some quantity, some integral, which should render you some physical quantity you would like to know, but it turns out that it's simply infinite. So integral is divergent. And this is a so-called problem of infinities. It arose just when people start to develop quantum field theories. So it's the very beginning, the early days of quantum field theory, it was already realized that there is such a thing as divergent integrals. And perhaps most sharply, this problem of infinities shows itself when people try to merge quantum field theory with the theory of gravity, with gravitational theory. And all our experience today shows that perhaps the apparent degrees of freedom which we perceive in a given quantum field theory, they do not provide, I would say, a proper starting point to building up the quantum theory. And this means that probably there is some hidden theory on the next level where the degrees of freedom, apparent degrees of freedom, should be reconsidered and should be recovered and understood in a different way from a new point of view. Therefore, hidden, as I said, on the existence of a new, so to speak, next level theory, which we still have to understand. And one of such, next level theories is a string theory. That is a theory of one-dimensional extended objects. And it offers a very intriguing possibility how to think about quantum fields in a very, very different way. And hopefully to construct the quantum approach, the quantum field theory, free from this problem of infinities. So in fact, the problem of infinities, known under the name renormalization, the topic known under the name renormalization, will occupy the second part of the course, the second semester. It will be one of the central topics which we will be discussing in the next semester. Now, perhaps for me, it's worthwhile to mention from the very beginning what is the main challenge of quantum field theory. So what is the main problem? At least in the framework of particle physics. So let me not to go to the condensed matter story, but just to say about particle physics. So concerning particle physics, the main goal is to be able to ultimately compute and predict physical observables, such as, for instance, cross ratios in scattering experiments, decay rates of unstable particles, and the spectra of bound states. These all are very difficult questions, theoretical questions, and this is because we don't have a direct access to local particle interaction laws. We don't know how to access these laws. What we can do, we can build up a theoretical model of interaction laws between elementary particles, and then test these predictions. For instance, in our colliding experiments, when we measure such things as cross ratios, experimentally measure such things as cross ratios or decay rates of unstable particles. Now, as I said, the present course is divided into parts. Formally, the first part is an introductory part, and the second part is an advanced part. And we start from a very important topic, namely discussion of symmetries. So symmetries play an extremely important role, not in a quantum field theory, but also in physics in general, in our life as well. Actually, probably we exist only due to the fact that there are symmetries around. And symmetries essentially mean that the laws of nature are not arbitrary from one space-time point to another space-time point. If you have a certain law which you measure at one space-time point, and you move away and you made the measurements in the other point of space-time, you better find something which is in agreement with your previous experiments, but not something arbitrary, subjected to new laws. So symmetries provide a certain order in our world, allowing us to talk about universal laws. Therefore, symmetries are very important, and we will start our discussion in this course from symmetries and their relations to conservation laws. This will be the so-called Noether's first theorem, and it will occupy one of the central points in our course. And then we will come to a traditional so-called canonical quantization of three main fields, namely scalar field, a spinor field, and the electromagnetic field. No, electromagnetic field you know very well. Scalar fields and spinor fields will be something perhaps new to you. Then the next thing will be the scattering matrix, or as people call it, S matrix. S means scattering matrix, S matrix. So we will apply our knowledge about quantized fields to computation, to evaluation of the scattering matrix of the theory called quantum electrodynamics. And quantum electrodynamics is the theory of electrons and photons. So photons and electrons constitute a theory known as quantum electrodynamics. And so our goal will be to compute the scattering matrix, or at least some matrix elements of this scattering matrix in quantum electrodynamics to understand how this can be done. No, and in the second part of the course, we will be dealing with more advanced topics. We will study the important tool of quantum field theory known as correlation functions. And correlation functions, we will understand how to compute them by using the so-called weak theorem due to weak. Weak is a name. It's not weak, it's weak theorem. And in the second part of the course, we will study more advanced topics, like, for instance, quantization of fields with a path integral approach, which is due to Feynman. So Feynman path integral, and also non-abelian gauge theories, which directly leads to formulation of the standard model of elementary particle physics. And probably, if time will allow us to do that, we will study the important mechanism called Higgs mechanism, which is the cornerstone of the modern particle physics, which is the cornerstone of the modern particle physics. And we will understand it probably from the point of view of particle physics, and also from the point of view, a little bit maybe from the point of view of condensed matter theory, where it is realized in the so-called Landau-Ginzburg theory of superconductivity. Okay, I will try to build up my lectures in such a way that they will be more or less self-contained. But of course, you are very welcome to study the literature. Of course, it will broaden your view on the subject. And what I can recommend to look at, there is a canonical book, standard book, which is used at the universities, at many universities. It is Peskin and Schroeder, how it's called. Let me see. It's called Peskin and Schroeder, An Introduction to Quantum Field Theory. Have you heard about this book? I hope some of you maybe have seen it. Yes, Peskin and Schroeder. It's considered as a modern book on quantum field theory, which basically contains all what you need to know about quantum field theory. There are other books which are, how to say, a little bit more student-friendly, I would say, more student-friendly. For instance, there is a recent book by Anthony Zeh called Quantum Field Theory in a Nutshell, from Cambridge University Press. Perhaps it's a little bit, more easier to appreciate the discussion there. And there are more, how to say, advanced books, like, for instance, if you take Landau and Lifshitz book, volume, which volume is it? Volume,
Three, maybe.
3 is quantum mechanics. 3 is quantum mechanics, but there is a volume 4. Let me see on my shelf. It is volume 4, yes, quantum electrodynamics. Volume 4, quantum electrodynamics. There is also a book, which is another book, which is typically studied in physics courses, master courses in Moscow University. This is a book, it's a fundamental book by Bogolyubov and Shirkov, Quantum Field Theory. And I personally also like old books like Bogolyubov and Shirkov, and there is another book, very, very, how to say, very good, good written, contains many computational details. It's a book by Sylvan Schweber. It's an old book, Sylvan Schweber. It's called An Introduction to Relativistic Quantum Field Theory. It's a thick book. It's like this, very thick. But it contains a lot of computations inside.
Excuse me.
Yeah.
Can you recommend quantum field theory for mathematicians, like Takhtajan quantum mechanics for mathematicians?
Yes, there is such a book, Quantum Field Theory for Mathematicians. Just a second. This is a book. It's on my shelf. I wonder if you can see it.
No.
I'm not
because
sure.
Of your background.
Yes, it is because of the background. In any case, I think what I will do a little bit later, I will just send you a list of books. I have a list of relevant books. No, actually, how to say, bibliography of books on quantum field theory and particle physics and quantum field theory and condensed matter physics, and then you will see what might be, how to say, more suitable for you to pick up. Yes, if you want.
That would be really helpful, sir. Thank you.
Sorry?
I said that would be really helpful, sir.
Yeah. I will do that. I will send you a list of books. But if you are a mathematician and you would like to approach a quantum field theory from a mathematical point of view, to go into mathematical justification, I mean rigorous justification of certain constructions, then you can certainly look at the book by Takhtajan. And it's called, actually, it's not quantum field theory, it's called quantum mechanics for mathematicians.
Yes, I read quantum mechanics. I like this book very much.
Yeah.
And I want something like this, but for quantum field theory. That's why I'm asking.
Yes, there is a book. Similar to Takhtajan's book. It also directed to mathematicians. Let me see. Just a second. Yes, it's called Quantum Theory for Mathematicians. And it's a book by Brian Hall, H-A-L-L, Brian Hall, H-A-L-L. It's called Quantum Theory for Mathematicians. So this is more than 500 pages. Yes.
Is it the one from Springer's?
Let me see. Yes, it's one from Springer. Exactly. It's one from Springer.
Well, sir, any ideas about the opposite? I mean, the physicists who are kind of struggling with their math.
Yes, but there is a very nice book which is kind of short, but it contains all, in my taste, all important topics of quantum mechanics, which prepare you at best for understanding quantum field theory. And this is a book by Fadeev and Yakubovsky. It's a student mathematical library, volume 47. Fadeev and Yakubovsky, and it's called Lectures on Quantum Mechanics for Mathematics Students. And I think Takhtajan's book, it's a little bit next level over these lectures. I mean, in complexity, in mathematical complexity. So it's easier. It's easier to understand and appreciate concerning quantum mechanics. But as I said, quantum mechanics is very important because quantum mechanics is a, how to say, is a background, is foundation, is one of the theories from which quantum field theory arose. Combining quantum mechanics with special relativity gives you a quantum field theory, in fact. So if you would like to, how to say, deeply understand what quantum field theory is, of course, the knowledge of quantum mechanics is very, very helpful. And if you want to do it at the, how to say, more theoretical level than experimental ones, of course, experiments are super important. Without experiments, we could not even think about quantum mechanics. It arose, of course, largely or basically due to the fact that we could measure something and which did not fit our expectations, which we could not explain by using classical mechanics and classical electrodynamics. Because of that, quantum mechanics arose, essentially. But if you'd like to understand, as I said, quantum mechanics, from theoretical point of view, to understand basic theoretical concepts and notions of quantum mechanics, then I would greatly recommend you these lectures on quantum mechanics for mathematics students by Fadeev and Yakubovsky. The book is relatively short, and this is very nice about it. So it's 200 pages. It's not 500, it's 200 pages. But it contains, in a student-friendly way, and on the other hand, with a mathematical enough rigorosity, the discussion of basic, main topics of quantum mechanics. That's why I find this book very, very nice. Now, of course, there is a standard book by Landau-Lifshitz. Sure, that's, you can always pick up and read it. But again, the book of Fadeev and Yakubovsky, it's oriented more on theoretically inclined students. Theoretically inclined students.
So there is one more book of Itzhak and Zuber, QFT.
Yes. There is a
It's also
book,
good.
yes, there is a book by Itzhak and Zuber. Yes. There are many books. That's called Quantum Field Theory, which you can also look. Another nice book is by Pierre Ramon. It's called Field Theory, a Modern Primer. It's also a good book. What I will also do for you, I will send you my lecture notes, which actually, in a sense, a book also, and they contain the material which I will be telling you. So that would be very helpful for you, I guess, not only to hear my lectures but also read and rethink what I will be talking to you, what I will be telling you during our lectures. Okay, do you have any questions? It was a sort of introduction discussing what is quantum field theory. As I told you, this is a tool we use to describe the physics of elementary particles. I told you about some basic books, but I will send you more extended lists of books, both in particle physics and in condensed matter. There is also, of course, application of quantum field theory to other subjects. Like, for instance, there is a specialization to the so-called conformal field theory, which is also very important. I think you might have a separate course on conformal field theory.
Yes, we have.
Yes, you do have. And there you, of course, also will meet quantum field theory as well. Conformal field theory is a particular instance or example of quantum field theory. It's also a quantum field theory in 2 dimensions. In 2 dimensions, invariant with respect to the so-called conformal group. All right, and after this little introduction, let me then probably start with the main subject of today's lecture, and this will be about classical fields and symmetries. So what I will be talking today, and probably during the next lecture, is an important desiderata, or if you wish, prerequisites for the study of quantum field theory. Before studying quantum field theory, you need first to understand classical fields. How do they arise, for instance, from classical mechanics? Okay?
Okay.
Good. Then I will do the following. I will switch on my camera and make the whiteboard on which I will be writing, and you will be then receiving the image of my whiteboard. Okay? And video, I will make a way so that it will not interfere with what I will be writing. We start from classical fields and symmetries. And this discussion includes the Lagrangian description of classical systems with an infinite number of degrees of freedom. And as I said, Noether's first theorem that allows to construct dynamical invariants, in other words, quantities that remain invariant during the time evolution of our dynamical system. Now, let me remind how in classical mechanics we can pass from discrete to continuum. And to describe continuous systems, like, for instance, vibrating solid, we need to make a transition from a finite number of degrees of freedom to an infinite number of degrees of freedom. And this means that we have to specify at least coordinates of all the points, and the number of these points is infinite, right? If we consider the substance like a solid rod, we need to specify an infinite number, the coordinates of an infinite number of points. But in fact, the continuum can be reached by taking appropriate limit of a system with a finite number of discrete coordinates. For instance, let's consider an elastic rod of fixed length which undergoes small longitudinal vibrations. So we have some system like a rod, and we assume that this rod undergoes small longitudinal vibrations, and we want to describe such a dynamical system in the framework of classical mechanics. Now, what we can do, we can approximate this system, this rod, by a system of equal mass m particles spaced at a fixed distance delta A from each other. So the system looks like this. You have a wall here, and then you have a spring, and then you have a mass, and then you have another spring, another mass, so mass m, and so on. Like this. Let's assume that the distance between these equal mass particles in the equilibrium position is equal to delta A. Let's assume that the distance is just delta A in the equilibrium positions, and we can enumerate these masses, like say 1, 2, and let them be n of them. So from 1 to n, and then the number of springs will be n plus 1, and so the length, the total length from one wall to another wall, L, is then equal to n plus 1, so the number of springs multiplied by delta A. Now, each spring we have to supply with a fixed Hooke's constant, and I will denote this constant by K. So K is a Hooke's constant. Okay, now we describe the displacement of ice particle from its equilibrium position by the coordinate phi I. So phi I is the displacement. So displacement means that we take our particle and move it a little bit away from the equilibrium position, and this deviation from the equilibrium position of ice particle is given by this value phi I. So it's a displacement. Now, the kinetic energy of these n particles is easy to write then. So kinetic energy is T, given by sum over all particles from 1 to n, m over 2 phi dot squared I. Phi I dot squared. So the standard kinetic energy of one particle, and then you sum up over all particles. And now we also know that there will be potential energy stored in these springs, and we have to compute it. So let's assume that we introduce a coordinate axis here along this line. This will be coordinate axis x, and the origin of the coordinate system we put here. So this point will correspond to x equals to 0. Then the coordinate of ice spring, the left end of ice spring will have coordinate xi equals to I delta A plus phi I. So we go delta A times to a position of ice, left end of ice spring, and then there is a deviation phi I. So this would be the coordinate of the left end, and then the coordinate of the right end. Right end will be xi plus 1, which is I plus 1 delta A plus phi I plus 1. This will be the coordinate of the right end of this string. And so the potential energy then stored in the I spring, let me denote it by UI. As you know from classical mechanics, is Hooke's constant over 2, xi plus 1 minus xi squared. So length of this spring squared, which is, if I substitute these expressions for the left and the right end, you will see that this is k over 2 delta A plus phi I plus 1 minus phi I squared. So this is our potential energy of one spring, and then we need to sum up over all to get the total potential energy. So the total potential energy is then given by the sum over all springs, and so this means that I'm summing from 0 up to n. This expression ki over 2 delta A plus phi I plus 1 minus phi I squared. And now it makes sense to open the square in the following way. So first I will write sum from 0 to n k over 2 I put in front, phi I plus 1 minus phi I squared. Then there will be constant term plus k over 2 plus k over 2 delta A squared n plus 1. So this is summation already done over all springs. It gives me number n plus 1. And then there will be cross term equal to k sum from 0 to n of delta A I also take away, phi I plus 1 minus phi I. So this is a cross term when I will open the square. And let me also associate phi 0, there is a phi 0, and phi n plus 1. So the left end of the first spring and the right end of the last spring, I put them to 0 because the walls are unmovable, which means that the left end of the very left spring and the right end of the very right spring, they are fixed. They are fixed, and they are fixed, meaning that fluctuations, displacements are not possible. And that's why phi 0 and phi n plus 1 I put to 0. So if I do that, then you see that actually this sum here is equal to 0, because the terms, if you write these terms explicitly one by one, you will see that they will start cancel each other. And therefore, due to this boundary conditions, phi 0, phi n plus 1 is equal to 0, then the whole sum is equal to 0. And so the kinetic energy, the potential energy is then essentially given by this term here plus some constant. But as you know, in classical mechanics, the constant shift of the potential plays no role, because the force is given by the gradient of the potential minus gradient of the potential, and that's why this constant is not important, and I will throw it away. Therefore, writing for the potential energy stored in these springs the following formula: 1/2 k sum from 0 to n phi I plus 1 minus phi I squared. So this is a potential energy.
Can you explain here why we have excluded the second term?
Explain. Sorry, say it again. Explain.
Why we have excluded the second term?
This one. You mean this one?
Right.
It's a constant term. It does not depend on phi I. It does not produce contribution, for instance, to the force, because the force acting on I's particle is given by minus derivative of the potential dui over d phi I.
Okay, understood.
And since term is constant, in a sense, it does not depend on phi I. It does not produce any contribution to the force. So if you compute this force, then you will see it is k phi I plus 1 plus phi I minus 1 minus.
Can we understand it by this way, like, because this is a classical field, so delta A should be very small, so we can neglect it so that only the first term remains here. Can we understand it like that?
No, that's what I'm not going to do. Well, at the end, I will do, in fact. I will send delta A to infinity, but this is not the reason why I'm throwing away this constant term. I'm throwing it away because it does not produce contribution to the force and to the equations of motion, because it is constant.
But it's also true, right, that delta is very, very small because it's a classical field?
Delta A will be small at the end for the reason because I will be making the transition to the continuum. And so I will make the distance between the particles in my description very, very small, actually going to 0. But simultaneously, what will be happening is that the number n will be growing, right? The number n will be growing. So I will be putting more and more and more particles and more sprints between these two walls. So on the other hand, delta A will be tending to 0, but on the other hand, as you will see, n will be tending to infinity. And I must consider a certain scaling limit in order to achieve a well-defined system in the continuum. And that is what
we can say that it's a general form of both classical field and quantum field.
Yes. Mm-hmm.
Okay.
Yeah. So this is a force. And this constant term does not contribute to the force. This is a standard thing in classical mechanics. So potential is determined only up to a constant shift. It's a standard thing in classical mechanics. You can throw it away because it produces no contribution to equations of motion of your dynamical system. It produces no contribution to the forces, and therefore it can be neglected. And so this force, you see, you can consider it as a result of the difference between the forces exerted by a spring on the right from I's particle, and this force is k phi I plus 1 minus phi I. This is how springs act on I's particle from the right. And then there is the action of a spring from the left on our particle, and the forces exerted will be given by k phi I minus 1. And the difference of these two, this is from the left, from the left, and the difference of these two gives us the force acting on this I's particle. Now, this means that we know kinetic energy, we know potential energy, and therefore we may write the Lagrangian for our theory. And you know from classical mechanics how to do it. So Lagrangian for our dynamical system of particles and springs is given by the difference of kinetic and the potential energy. So it's t minus u, and therefore I can write that this is sum from I is equal to 1 up to n m over 2 phi I dot squared minus potential energy k over 2 sum from 0 to n phi I plus 1 minus phi I squared. And so far we have our system with finite number of degrees of freedom. And these degrees of freedom, they are described by these displacements phi I. And this is a classical Lagrangian for this system. Now what I would like to do, I would like to take a continuum limit by sending the number of particles to infinity. So the number of strings goes to infinity, but simultaneously I put delta A to 0 in such a way that the length given by the formula n plus 1 delta A will remain constant. So this limit is special. You see, delta A goes to 0, n goes to infinity, but in a consistent way, such that n plus 1 multiplied by delta A is kept fixed. Now you understand that increasing the number of particles means increasing the total mass of a system, because every particle has a mass m. And now I'm putting more and more and more particles, actually infinite number of particles, and this means that at the end, the mass of my system will be infinite. In order to prevent this infinite mass and to keep the mass of my system finite, I will assume that mass goes to 0 in a way consistent with delta A, such that the mass density, mass divided by delta A, will go to a constant value called mu. And this is constant mass density, constant mass density, which I expect to find in the limit. Mass density in the limit. Constant mass density. Also, I would like to keep the force between the particles finite, and for that I need to assume that my Hooke's constant k scales with delta A in such a way that k delta A also goes to a finite constant, which I will call kappa. And so this my assumptions about the limit which I'm going to take. And in order
instead of Lagrangian, shouldn't we should take Lagrangian density, right? For this?
Yes, we can just make this limit on the Lagrangian. And this is what I'm going to do now. And for that, I need to rewrite my Lagrangian in a little bit different way. So I will just, it's the same Lagrangian, but first I write it in the following way. So I say
excuse me. How can k times delta A tend to some constant kappa, because k is constant and delta A tends to 0?
So k scales. Now k is not a constant anymore. It's called the Hooke's constant, yes. But I will make it dependent on delta A in such a way that k delta A will turn to kappa. So kappa, if you read, it will scale like kappa constant divided by delta A. So now I make it delta A dependent.
Okay, thank you.
Right. So in a way, this will keep the local interaction between the particles constant, even in the limit when we make a number of particles infinite. So we make them continuously distributed. Sprints in a way never disappear because there is always a tension between the particles due to the fact that you keep this Hooke's constant in a way. Now it is replaced by kappa, which you fixed, which you keep constant, which you would like to keep constant. Good. So what I will do now, I will just formally rewrite the same Lagrangian by introducing delta A inside. So I write this in the following way. So I multiply with delta A and divide mass by delta A, and then there is phi I dot squared. So this is kinetic term. I did nothing. I just introduced delta A and I divided by mass by delta A. And concerning the potential, I do the following. So sum from 0 to n. And I write delta A multiplied k delta A. So in fact, that means I introduce delta A squared. But then in this part, which involves phi I divide by delta A, and then I take square. So in fact, I did nothing for the moment. Now, taking the limit, what I would like to do, and I would like to take my limit, delta A to 0, under the conditions which I have indicated, keeping constant mass density and keeping constant hook constant in the limit delta A to 0. What I will do, and this is a very important step, I will replace now the discrete index I of my displacement variable by a continuum variable x. So in other words, what I will do, I will pass from phi I to phi, which will depend on I delta A. And this I delta A, I will call the continuum variable x. So this is phi on x. Where in the limit which I'm discussing, phi x becomes a field. Becomes a continuous field depending on this variable x. And also you see then what happens is that phi I plus 1 minus phi I divided by delta A, where it will go under this identification, it will go to phi x plus delta A minus phi on x divided by delta A. And in the limit delta A going to 0, where this ratio goes, you know very well where it goes. Delta A to 0, limit.
Infinite.
It gives?
Why not?
Infinite.
It gives a derivative, right?
Yeah, derivative. Sorry.
It's a derivative.
Right.
Yes, it's a derivative. dx, I write it as a partial derivative because we will have also dependence on time. So it's a partial derivative with respect to variable x of this field phi on x. This is where it goes. And so now looking at this Lagrangian, you see that in the limit delta A to 0, where it goes, it's 1/2 sum from 1 to n or from 0 to n. In the limit when n tends to infinity, this is not important where you sum, so you can write the whole, from 0 or from 1, you can replace it by integral from 0 up to L. It's a replacement of a sum. Delta A will go to the differential delta x. And the first term here, kinetic one, m divided by delta A will go to mass density mu. Phi will remain, but it will become now phi on x, and derivative with respect to continuous time variable will remain. So there will be mu phi dot squared. And from this potential term, we will get k delta A here will go to our parameter kappa. And the first derivative of phi with respect to the variable x squared. This is now how continuum limit of our dynamical system looks like. You can also pass to equations of motion. You can also make this limiting procedure at the equations of motion if you take our discrete Lagrangian and write down equations of motion which come from it. They will look like m delta a phi double dot I, so double dot with respect to time, minus k delta a, and then phi I plus 1 minus phi I, plus phi I minus 1 minus 2 phi I. That's what comes from the potential term, divided by delta A squared is equal to 0. There are discrete equations of motion which follow from our discrete Lagrangian. And now using the limiting procedure delta A to 0, well, you see first of all that lim delta A to 0 applied to phi I plus 1, phi I plus 1 plus phi I minus 1 minus 2 phi I divided by delta A squared. There is nothing else as the second derivative of field phi in the continuum. So this limit is equal to second derivative of phi with respect to x, or which you might denote as simply dxx phi, like this. And so in the limiting case, you just get equations of motion mu phi double dot minus kappa second derivative of phi with respect to x is equal to 0. That is equations of motion you find in the continuum, starting from the discrete equations of motion. But of course, you may derive the same equation just starting from this Lagrangian, continuum Lagrangian. There is this means that in fact you can represent your Lagrangian, and this is something which we will always do in quantum field theory later on. You represent it as an integral over dx from 0 to L of what is called Lagrangian density. I always will denote it by this curly L. It's called Lagrangian density. Lagrangian density. And in the case at hand, in one which we have here, you see that the Lagrangian density is given by the formula 1/2 mu phi dot squared minus kappa dx phi squared. This is Lagrangian density in our case. Now, you know that there is a very important notion of an action. An action, because of the action principle in classical mechanics, and the action is an integral of the Lagrangian with respect to time. And so we may now pass to the general picture. We say that we're dealing with an action for our dynamical system, continuum dynamical system. So action S is a functional of our displacement field phi. Phi is a displacement field phi depending on x and t, on two variables. And as I said, first of all, it's an integral with respect to time from t1 to t2 of our Lagrangian. And Lagrangian itself is an integral with respect to space variable dx, x is differential dx, of the Lagrangian density. Let me write it here, multiplied with Lagrangian density. And Lagrangian density, it's a function, in our case, of field phi on xt. It is also involves its derivative, phi dot, first derivative with respect to time. And it also involves the first derivative with respect to x variable. So it's a general construction. S is a functional. Functional means that it's a map which takes a function and returns you back a number. Yeah, number because you are integrating now the Lagrangian density, which is a function of phi dot, and dx phi over both over space and over time. So at the end, you just get a number. And this is your action functional. Now, to obtain the equations of motion directly from this Lagrangian equations of motion for this displacement field, you need to understand how this action changes under an infinitesimal change of the field. So you do infinitesimal change of the field. So phi on xt, you replace by phi on xt plus small addition delta phi on xt. By the way, this procedure, which I'm doing here, is called variation. So what I'm doing here, I'm varying my action. So I'm adding to phi on xt an infinitesimal shift delta phi on xt. And then I see first how derivative change, and they change accordingly, namely derivative with respect to time, phi on xt changes to d over dt, phi on xt plus d over dt, delta phi on xt, and analogously for derivative with respect to x, plus d over dx, delta phi on xt, like this. And then you see how your action responds to this infinitesimal change of the field phi. So what you do, you compute delta s on phi, so change of the action, by taking s on phi plus delta phi and subtracting from it s on phi. That is a very well-known procedure of varying a functional in mathematics, or also something which hopefully you have seen and you have learned from the course on classical mechanics. So this gives me the following. This is first double integral t1 t2 dt 0L dx. So integrals are left over. And then varying the Lagrangian density, I can do the following. I differentiate Lagrangian with respect to the field phi, and then multiply it with delta phi, because delta phi is very small. So changing phi by delta phi means that I may replace this at first order in delta phi by just derivative dl over delta phi multiplied by delta phi. Then I differentiate Lagrangian density with respect to velocity of the field phi. So it means with respect to phi dot, and then dt acting on delta phi. No, and plus the last term, I differentiate my Lagrangian. Let me write it probably on the next line. I differentiate my Lagrangian with respect to derivative of phi over x, and then dx acting on delta phi. Next, what I will do, I will integrate these derivatives over time and over space by parts. And so I will get therefore two kind of terms. First, I get a bulk term where now derivatives will be acting, time derivative and x derivative will be acting on Lagrangian derivatives. So I will get bulk integral. t1, t2, dt 0 L dx, and then dl over d phi, and now minus dt acting on dl over d phi dot, minus dx acting on dl dx phi, like this. So this is a bulk term, but then I will also have boundary terms, right? As usual, you must have boundary terms. And so the first boundary term, you integrate over L, and you are left with one integral from 0 to L, dx, and then dl over d over dt phi, evaluated, delta phi evaluated in the substitutions t equals to t1, t equals to t2. So this means that I have taken the integral, the integral of the total derivative over time. Yes, and I will get them left, and I'm left with one integral over x. And now the integral is evaluated in the substitutions. T is equal to t1, t is equal to t2. But then because of also derivative with respect to x, I will get another boundary term, which is integral this time from t1 to t2 dt dl dx phi, like this, evaluated in the substitutions. X is equal to 0 and x is equal to L. So in other words, this quantity now and delta phi as well here. Now this quantity now is evaluated at the end points of the elastic rod. So at the walls, if you wish, walls equals x equals to 0 and x is equal to L. Now there is a certain difference between these two boundary terms which we have obtained. And here, by the way, I forgot to multiply with delta phi. Delta phi is still there. After integrating by parts, delta phi is left over. Now derivatives are acting on these Lagrangian derivatives. Yeah. Now, yeah, maybe let me first say something about the bulk term. To find, as you know, to find the trajectories of the dynamical system, we have to minimize the action, which is a principle of the least action. Better to say extremize the action, which means that we have to put to 0 the variational derivative. Delta S over delta phi, we have to put to 0. And these are equations of motion for our system. But we have to do it under the condition that the value of the field, the values of the field at the initial and finite times are unaffected. So in other words, delta phi on x t1 equals to delta phi on x on t2 must be equal to 0. That means that initial profile of our field and the final profile of our field must be taken intact, must be kept intact. So this means that variations which we perform on our field phi must be equal to 0. So in class,
can you repeat this field? Repeat this point?
Yeah. So maybe I will draw what I'm doing. So you have a say in classical mechanics, you have a particle which moves from one point to another point. And so it makes some actual trajectory. It moves, say, in some potential, it interacts with this potential, and it moves over a definite trajectory. What we do in variational principle, we say, okay, we keep initial point of a particle and the final point of a particle fixed, and a finite position of a particle fixed, and we are trying all other trajectories which are in the neighborhood of our actual trajectory. And for all these trajectories, the principle of the least action is telling us the value of the action must be larger than the action, the value of the action on the actual, in my case, red trajectory. But this comparison of the value of the action on the virtual trajectories and on the actual trajectory is made under the assumption that the initial and the final points reached by particle or taken by particle, they are kept fixed. Okay? So initial and the final positions of the trajectory, I don't vary them. They are always fixed. I'm drawing different trajectories, but initial and the final point are kept fixed. The same thing happens for a field. So what is a field? You can imagine it in the following way. So suppose you have time, initial moment of time, t is equal to t1. T is equal to t1. Then at t is equal to t1, our field phi on x has a certain profile. Let me draw it like this. It's a profile. It's phi on x on t1. Then it's an initial, it's a point x is equal to 0, say, and this is point corresponds to x is equal to L, and this is a certain profile. So profile for a function phi on x t1. Then when time grows, our fields start to move. So if you wish, from the point of view of this picture, it starts to span some surface. Where t is equal to t2, you have another profile. Again, this point corresponds to s equal to 0 and x is equal to L. Okay? So it sweeps a certain surface in this case. And this surface is an actual trajectory of this field. So maybe I should draw this in red again. In red. Now, in this variational principle, which I'm explaining now for the case of the field, what you do, you are comparing the nearby surfaces. You excite this surface, but exciting another surface on which you would like to compute the value of your action functional, you still keep the initial profile of the field and the final profile of the field the same for all the surfaces, for all virtual surfaces on which you would like to compute the value of your action and compare it with the value of the action on the actual trajectory of this field. This means that at t is equal to t1 and t is equal to t2, the variations, which means deviations from the actual trajectory of my field, are put to 0. In other words, at t is equal to t1 and t is equal to t2, I'm not varying the profile of the field. Okay? And this is again, just let me repeat that this is a standard condition which you always use when you derive equations of motion. You keep initial and the final profile of your configuration fixed. You don't do anything with it. That's why delta phi on t is equal to t1 and t is equal to t2 is simply put to 0, which means essentially that this term here is equal to 0 by the condition imposed in the derivation of the equations of motion. So this term is 0. What about the second term, the second boundary term? Now this term can be put to 0 or not put to 0 on physical grounds. Here physics comes. You have to specify these boundary conditions from physics. For instance, if we say that we are dealing with a rod which is clamped, rigidly clamped between these two walls, and walls are rigid, they are not movable, this means that at x is equal to 0 and x is equal to L, the profile of my field is kept fixed, which means that delta phi on x is equal to 0 and delta phi on x is equal to L is equal to 0, which means unmovable walls. Walls are fixed, they are not movable, they are rigid. So I cannot fluctuate field at x is equal to 0 and x is equal to L. This is not possible because the walls are rigid, and this is physics. This is a physical requirement. In principle, you can make these walls movable, then it will be a contribution from this boundary term. But if you say that these walls are rigid, so they are not movable, then this term vanishes as well. So this vanishes from physics. Physics assumption, which kills this term. So this means that one boundary term vanishes because of the requirement of deriving equations of motion, and the other term vanishes by the physics requirement of rigid walls. And so you're left just with a bulk term. And for an actual trajectory, the vanishing of delta S for any variation delta phi by the basic lemma of variational calculus, which might have heard about in the course of mathematical analysis. By the basic lemma of variational calculus, it means that such situation is possible only if what is written in the square brackets vanishes. And what is written in the square brackets and what is vanishes is exactly represents equations of motion for our dynamical system. And so written explicitly, let me take another page because it's not, no, it's still moving. Okay, so let me write then. Let me write them. Equations of motion which follow from this bulk term, or in fact this is a bulk term, d over dt, derivative of the Lagrangian with respect to dt phi, plus d over dx, derivative of the Lagrangian with respect to dx phi, minus derivative of the Lagrangian with respect to d phi is equal to 0. And these are equations of motion derived directly from our continuous Lagrangian by using essentially the basic lemma of variational calculus and our considerations of the boundary terms. And so if we now apply these equations of motion to our concrete problem, plug in our Lagrangian density here, then we will get the following equations of motion. I have written them down already, starting from the discrete description. And if you do it now here from this Lagrangian, differentiate Lagrangian density, you will find the following expression. dxx phi is equal to 0, where c is a square root of the ratio of kappa to mu. And this square root of the ratio kappa to mu, you can check that this quantity has a dimension of the speed, and this speed is nothing else as a propagation velocity of vibrations through our rod. So this is propagation velocity. Propagation or velocity of propagation of our excitations through the rod. Propagation velocity. Now, the equations which we get here for this particular dynamical system are very easy, and you see they are linear. They are linear. And for linear equations, you know that superposition principle works. And so we can solve these equations by making the following ansatz. Phi on xt is exponential I px, and then ap depending on t, coefficient depending on t, plus another minus ipx bp on t. So I take a particular ansatz for my solution, and then I will impose the condition that at say x equals to 0, so phi on t for all the times at 0, phi remains to be 0, which means that I'm on the left wall, and on the left wall field phi is not excited, so it keeps the coordinate of the left end, which is 0. And then if you substitute it here for x, you see that it gives you immediately the condition that bpt is equal to minus apt. P here is a parameter for the moment, it's just a parameter. And if you plug it in back here for BP in this formula, you see then I can a bit specify this formula further. I can refine it and write the expression that phi on xt is given by an ansatz apt multiplied by sine px. So the sum of these two exponents, or better to say difference because of the minus sign here, the difference of these two exponents can be replaced by sine px. Division by 2 is not important. I just consider here as another coefficient apt. And now if we require that also the right wall is rigid, so phi on lt is equal to 0. This means that now I'm dealing with the condition apt sine pl is equal to 0 for all t's. So the only way is that sine pl is equal to 0. And that gives me a solution for p. You see that from this equation here, p must be actually associated with pn, which is given by p pi multiplied by n divided by l. So pi is our famous number 314,926, and so on. Pi n divided by l. So now we can take this ansatz and plug it.
It's like an infinite potential.
Sorry, say it again.
So it's like an method of infinite potential will.
Yeah, in a sense. Okay, and then what we do, we take these ansatz and plug it into equations of motion. So here, and in this way, we give time evolution for equations for a time evolution of these coefficients AP. So AP or APN, no AP, we can plug just this ansatz right away in this formula and get AP double dot plus C squared P squared multiplied by AP on T is equal to 0, right? So here we have, you see, we have double derivative in x. When we differentiate sine, it will give us cosine. Then we differentiate cosine once again, because there is a second derivative here over x. It will give us minus sine. So and p getting out twice. So the minus sign here will be replaced by plus c squared will be left over, and there will appear p squared after double differentiation over x. And so this is the evolution equation for these coefficients AP, and this we can immediately solve. You know how this equation is solved. APT is immediately given by exponential I omega PT AP, where omega P, omega depending on this P, is given by plus minus CP. Yeah, you see immediately that what I'm writing here is solution where AP is a coefficient which is time dependent. So this is how this equation is solved. And now, you know, for any Pn, so in other words, for any n where n is an integer, for any integer n, I will get a solution of my equations of motion. But as I said, since equation is linear, a sum of two solutions will be given a solution. So that's why I can just sum up over n and produce a general solution for this system. And so that's why I can write for phi on xt a general solution in the following form: sum over n integers, sine p and x, and then sum of two coefficients, an cosine omega n t plus bn sine omega n t. And the sine cosine, they replace this exponential omega I omega pt for two, because omega p is taking now two values, right? Cp. So in one case it's plus Cp, in the other case it's minus Cp, and that's why these two exponents can be replaced in the standard way by cosine and sine. And so this is how the general solution looks like. By the way, it's enough to sum over only over positive integers from 1 to infinity, because when n is negative, then because of the sign here, this will just produce a negative sign, overall negative sign, which you can embed into the coefficients an and bn. So it will not produce a new solution, because change of the sign in front of sine p and x can be observed into coefficients an and bn. So this is how the general solution looks like. N is equal to 0. Well, you can include it, but for n is equal to 0, you have a 0 solution, because sine of 0 is 0.
Shouldn't we also check the boundary condition for t equal to 0?
Yes. That's why you are still left with this infinite set of numbers an and bn. So an and bn, they for the moment are left undetermined. So an and bn are undetermined, but they will be determined if you specify the initial value of the field at t is equal to 0. And if you specify, so you specify t is equal to 0, the initial profile, you need to give an initial profile. So initial data, phi on x0. And at t is equal to 0, you also need to give the derivative of the field phi. So you need to know the field and its velocity, as usual, position and velocity. And position and velocity, you know, in Newtonian mechanics are needed to produce a unique solution of the Newton's equations of motion, right? You need to know position and velocity, because equations of motion are of the second order. And absolutely the same situation arises here. Equations which we are dealing with, they are second order in time derivative, and therefore to uniquely specify a solution, we need to specify the initial position of our field and the initial velocity. And from this data, specifying initial position, initial velocity, we then, if we wish, we can uniquely determine these coefficients an and bn. So what we need to do then, we need to take this field phi on x0 and phi dot on x0, expand them in Fourier series in this sign p and x variables, and then compare at t is equal to 0 the coefficients in these expansions and identify what are these an and bn. And that leads to a unique solution of this problem. Now, I think at this point, what we have done, we have completely described our dynamical system in the continuum. So let me just briefly repeat what we have done. So we start from a discrete system, and then we increase the number of degrees of freedom, and we smoothly pass to the continuum by requiring certain scaling properties of our coefficients, like mass, like Hooke's constant. Then we obtained the Lagrangian in the continuum. And we see now that we describe our system suddenly in terms of the field, the function of two variables, of space variable x and the time variable. And what we also discussed, we discussed the principle of the least action. So we extremize the action functional for this field, and we derive the corresponding equations of motion, which we, as we have seen, under specifying initial and boundary conditions, lead to a unique solution of our problem. We completely restore from these equations the displacement field. So in principle, this is a way how dynamical systems, continuous dynamical systems, or dynamical systems in continuum, are described in classical mechanics. And for us, the concept of a classical field is important because this is something, some background notion we will be using further for quantization. Okay, I think for today that is enough. So I think somehow my time is up for today. So we will continue next Friday by discussing, I think, the Lorentz and Poincaré groups first, which provide an introduction to basic symmetries of quantum field theory. But for today, that is all. If you have certain questions, please ask.
Yeah, so we derived Lagrangian density like kind of synthetically when we took a classical system and made some scaling limits, as you explained. But when it comes to general Lagrangians, for example, for Young-Mills or for, I don't know, Dirac theory, how do we derive them? Because we are usually given a Lagrangian, but how like people got it?
People got it. So the basic thing, how it happens in classical mechanics, of course, the concept of the Lagrangian concept was derived by departing from Newtonian mechanics. So principle of the least action appeared later. First, there were Newton's equations and nothing more. And Newton's equations, this is a, if you wish, how to say, abstraction which you derive from all experimental data, right? So Newton's equations is the results of experiments. So then formally you see that Newton's equations can be derived from the variational principle. And then what people notice is that variational principle has a universal character. You can extend it, for instance, for the case of electrodynamics, where the main equations are Maxwell equations, but it appears that you can also derive them from the action principle. And so this means that the action principle becomes universal, and you would like to appeal to it. So then the goal is somehow to use certain physical properties of the system and understanding of what the system is, somehow to guess what would be the action for the system, which leads to the dynamics, which leads to right equations of motion, in a sense that it reproduces a certain physical properties of your system. And in a way, I will discuss in a very detail how Dirac derived his equation. I will explain to you that Dirac's equation arose from an attempt to overcome the problem with negative probabilities. Originally, people wanted, for instance, to write this equation as a natural generalization of Schrödinger equation to relativism, to make it relativistic. But that did not work because it led to the problem of negative probabilities. And we will discuss it during the course, how this problem arose. And this is what Dirac struggling with. And this is what led to the appearance of a new equation. But first, there was a Dirac equation, which is an equation of motion, if you wish. It was not an action. If you have equations of motion, then you can ask a question from which actions they come from. You see, but first there was an equation of motion, which he derived by trying to invent a relativistic theory of electron free of the problem with negative probabilities.
Yeah, here it's quite clear, but yeah, like in Dirac's case, it's quite clear, but when it comes to like some general stuff like, well, young males or some gravity, how was it there then?
Principles of symmetries play an important role. For instance, in general relativity, you need a general covariance. And this is a very, very strong requirement. You cannot write more or less arbitrary Lagrangian depending on the metric. It will not be covariant. You need to find covariance with respect to, or invariance with respect to general coordinate transformations, which we then put in the form of the equations of motion or in the form of the action. The same idea is non-abelian gauge fields. You need to find invariance of the non-abelian gauge transformations. Invariance, so symmetries enter and start to play a super important role in search of your invariance and therefore objects which can describe your dynamics. This becomes a guiding principle in this case, you see?
Yeah, thank you.
Mm-hmm. That's very important question. Thank you. But we will see how it will work and why. So first you find the symmetry transformations, and after you find the symmetry transformation, or you declare something to be a symmetry, then the next natural step always is to try to find invariance of these symmetry transformations. This is how the general idea, this is what is the general idea behind this.